So we're going to start combinatorial algorithms, the course, by maybe one of the most classic combinatorial algorithmic questions, and that is bipartite matching. Okay, so what is bipartite matching? What is the problem? Given a bipartite graph G equal to, I like to call the sets L, R, and E. So meaning that L is the left side, R is the right side, E are the edges. Given a bipartite graph G, compute both the size and the matching. Compute the size, the matching of maximum size. Okay, this is the problem of maximum matching. And just to recall, a matching is a set of edges, whose endpoints are mutually disjoint. Right? That's what a matching is. So we're going to study the problem of bipartite matching. And my first question is, do you know of an algorithm that can solve this problem in polynomial time? Max matching, bipartite matching. Any suggestions? Any suggestions? Have you seen this problem before? So let me, raise your hand if you've seen this problem before.
I have an idea on the algorithm, though.
I've not.
Okay, you have not. Someone has an idea on an algorithm. Go ahead.
Wait, I didn't fully. Okay, I was gonna say, is there, and choose two, like you can, the brute force case, consider all possible sets of edges?
You could do that. That would be an exponential time algorithm. That would be exponential time, right? Because the number of subsets of edges would be like 2 to the power of the number of edges. Is there a polynomial time algorithm for this? All right, raise your hand if you've seen max flow. Raise your hand if you've seen max flow. Okay, more of you have seen max flow. And so you may recall that you can solve bipartite matching through max flow, applying a max flow algorithm. So someone who's raised their hand on bipartite matching, do you want to comment? Any suggestions? All right. So just to get our notation in place, n is the number of vertices, m is the number of edges. I will always assume that the graph is connected unless otherwise stated. So the number of edges is at least the number of vertices minus 1. And so hence, essentially m is omega n. So I'm not going to carry dependencies of m plus n, I'll just say m. Okay, so if you recall your undergraduate algorithms, you may have seen something called the Ford-Fulkerson algorithm. The Ford-Fulkerson algorithm for maximum flow. Okay, raise your hand if you've heard the term Ford-Fulkerson. What?
Yes.
Yes, okay. Okay, those of you who've taken 201 or 102 should have seen this somewhere in your course. So the Ford-Fulkerson algorithm can compute a max matching. And when I say max, I mean a maximum matching, not a maximal matching. A maximum matching, so the maximum is the matching of maximum cardinality. So you can compute a maximum matching in O of Mn time. It's okay if you don't remember the Ford-Fulkerson algorithm or you've never seen it before, because essentially the point of today's lecture is for me to unpack the Ford-Fulkerson algorithm and show you some remarkable results about bipartite matching, which is one of the most fundamental combinatorial optimization problems. Okay, so the way that Ford-Fulkerson works is, one way to think about it is it takes the bipartite graph. So here is L, here is R. It's going to create a super source vertex called S. It's going to direct edges as follows. So from S to L and from R to T. S to L and from R to T. The capacities on each of these edges is 1. And then it's going to take all the edges of the bipartite graph, direct the edges as follows, and put capacities of 1 on all of them. And then the maximum flow here is exactly the maximum matching. Right? Because if you pump 1 unit of flow through this edge, then it has to take one of these out, and every flow path gives you a disjoint edge, and so the flow is a matching, and the maximum flow is the maximum matching. Any questions?
I don't know if this is just on my end, but the video quality is really grainy right now.
Yeah, I can see it's out of focus
It's
for
out
me
of
as well.
focus. Is that better?
Not really.
Not really? Let me see if this works. So it seems to be clear at my end. Hang on a second.
Signal issue. Like, it's really grainy. The resolution's low.
What about this? Is this better resolution?
Looks a lot better.
Yeah.
A lot better.
Okay, so this might be the trade-off. I mean, the resolution might be higher, but then the lag might be higher. So we'll have to see. On the other hand, is it laggy? Moving it around a bit.
I think it's fine.
It's fine?
Still with the lag.
Okay. All right. So, any questions about this? So please, go ahead and ask me questions. I'm still trying to gauge, what your background is. And so the more questions you ask me, the better I can gauge and the better I can sort of guide the lecture. So,
could you scroll up for just a little bit? I'll just take a screenshot.
Sure.
Just the first part.
Sure.
Thank you.
Are you going to be providing the notes you're taking, or should we be writing the notes as well down?
I will scan all of this and make it available to you.
Oh, okay.
I will scan all of this. And depending on the topic, I may even write extra notes on LaTeX. Yeah. I will scan. All of this will be available. So.
Can you cover why, in the algorithm you just described, it sounds like the discovering of the edges between L and R that are mutually disjoint is what we're trying to solve, but you had just drawn them as if they exist like I don't know. I guess I don't understand. I thought that would be what the algorithm's solving.
So I have just described the flow problem, and I'm using a max flow algorithm. Now, how the max flow algorithm works, yeah, if you've seen Ford-Fulkerson, you would see it. If you have not, then that's okay. I will explain sort of how Ford-Fulkerson works. The point is that this is just some sort of flow problem that is set up, right? So you take the graph, you assign these capacities, and you solve max flow on it. When you solve max flow, then you basically get a max matching. So what I will do is I will unpack the algorithm and explain how the algorithm works. Does that answer your question?
Somewhat. I guess the follow-up is, so if there wasn't a if there was an edge from L to itself, why does that interrupt max flow? Like, my understanding of flow is you're adding up the weight of the edges, so it would just still be another weight that you add on?
The graph is bipartite. So there are no edges within L or within R.
Oh, I see, okay.
Right, all the edges, so this is bipartite matching. General matching, this idea will not work. For matching in general graphs, we will talk about that in subsequent lectures. Okay, questions? Okay, so let's unpack or understand Ford-Fulkerson properly. Ford-Fulkerson for max matching. And if you haven't seen Ford-Fulkerson, don't worry about it. We're going to sort of rederive a lot of things about Ford-Fulkerson. But here's how the algorithm works. So at some stage, there is a matching M. And our aim is to increase the matching size. Okay, so our aim is to increase the matching size. And how is this going to work? So let's see what Ford-Fulkerson basically does. So here is our bipartite graph. And let's just say I'm going to draw the matching in red. So there are these matching edges. And these are directed backwards. We're going to direct these backwards. All other edges are going to be directed forward. So this is what Ford-Fulkerson is going to do. It's going to direct all the other edges forwards, while the matching edges are directed backwards. S is only going to have edges to the unmatched part, and the unmatched part has edges to D. So this is the current situation we're in. I'll just write it out here. So direct M edges backwards, disconnect matched vertices from S and D, direct all other edges. So by backwards, I mean right to left. Right to left, and direct all other edges from the left to the right. Okay? Now find what, this is what Ford-Fulkerson does. It finds what's called an augmenting path. Which is a path from S to T. It's going to find an augmenting path. So what does this augmenting path look like? Ignoring the part from S to T, it's going to start from some vertex here, get to some vertex here, as follows. So it's going to start from some vertex. This is not matched. It's going to take some forward edge. That's one of these edges. Then it has to go back, and the only edges that allow it to go back are the matching edges. So it's going to take one of these edges, then it takes a red edge, then it takes another edge, and then a red edge, and finally it reaches another vertex that is not matched. So just imagine this procedure. Like if you've seen Ford-Fulkerson, then maybe you recognize this. If you haven't, consider at some point there is some matching. So direct the matching edges backwards, disconnect them from S and T. Direct all the other edges forwards, and then you just find a path that goes from the unmatched side on the left to the unmatched side on the right, a directed path. And that directed path is going to look something like this. How many edges are in the directed path? Is it odd or even?
It would have to be odd, right?
It would have to be odd. Why?
If it's even, it would just go back to the initial position, and that would be not what we're trying to do here. It wouldn't be a path. It would just go back to the original position.
Well, not necessarily the original position. It could come back to here. Like it could be this. Like this has an even number of edges, but it doesn't reach the other side. So you have the basic idea. You need an odd number of edges to reach the other side because the graph is bipartite. Right? It's a bipartite graph, so you need an odd number of edges to reach the other side. So there are an odd number of edges, and if you observe, the number of red edges is strictly less than half of the path length. Right? So this is a path of length 5 and there are 2 red edges. If you had a path of length 7, you'd have 3 red edges. You'd have basically the floor of half. If you had one edge on the path, then you have no red edges. Does this make sense? Any questions?
Why is there ever more than one red edge? Like when you take one matched and then you go back to the right side, aren't you always then finding an unmatched vertice?
Good question. So actually, but the edge you take might actually go this side. It might go to there. You have edges in this region as well, right? In your graph. So you could have other edges that are directed as follows. So the red edges take you back. The forward edge may take you outside. It may keep you in the same region. And so you're going to keep bouncing back and forth over here until at some point you finally escape.
And then how do you start with the first M edges?
You're building it iteratively. So initially M would be empty. I'm going to describe a procedure that's going to increase the size of M, and then you do it by induction, or you iterate, or by recursion, whichever way you wish to think about it, and you're going to slowly build the M. Questions? Okay? So once you have such a path, you can flip to increase the matching. So what is the flip going to do? It's going to basically switch the matching edges to these. Now note that instead of there being 2 matched edges, now there are 3 matched edges. And I preserve the fact that this is a matching. These 2 were not matched before, now they are matched, and everything else stays as it. Every other vertex that was matched remains matched. This flip has increased the matching. And so whenever you can do the flip, you increase the matching, you change M, and then you repeat. This is the Ford-Fulkerson algorithm unpacked. Any questions?
Is the path we choose anything?
The path can be any arbitrary path from S to T, any augmenting path. Like essentially, as long as you find any path of this form, you can perform the flip.
Okay.
Right? Okay, question, how do you find such a path? How would you find such a path? By the way, I hope this is clear. What do I mean by not matched? It means this vertex does not participate. Doesn't participate in the matching M. Right? That's what it means to be not matched.
Can you just re-describe what does matched mean again? Sorry, I forgot already.
So yeah, your aim is to find a matching. And a matching is a set of edges whose endpoints are mutually disjoint. So this is what a matching is. You're given a bipartite graph, you're trying to find a set of edges of this form. So any vertex that is participating in such a red edge is matched. And any vertex that is not participating is not matched. So your aim is to match the maximum number of vertices.
And when you say mutually disjoint, meaning a vertex can only have one edge then coming out of it?
The endpoints are mutually disjoint. So a vertex is only allowed to participate in one matching edge. Okay, any questions? So when you do this flip, you can increase the matching, and then you can just keep repeating this procedure, right? You can essentially, now you have a new M, you go ahead and direct the M edges backwards, you disconnect the match, disconnect the match vertices from S and T, you direct all the other edges, left to right, forward, and you repeat this process. How do you find an augmenting path? So in general, how do you find a path in a graph? Like if you have 2 vertices in a graph, and you need to find a path from one vertex to the other, how would you do it? Okay. Any suggestions?
One simple way is BFS. You just expand to the next set of neighbors and
BFS.
Continue until you find.
Yeah, BFS. BFS or DFS, right? You can use BFS or DFS and you can find such a path. Exactly, right? So essentially you can find such an augmenting path in linear time. You can just do BFS, DFS, anything of that form. So this is the basic idea of Ford-Fulkerson. So what I want to do now is to talk about this in a much more formal and mathematical way. And in that process, we will discover, I'll prove, some fundamental theorems about matchings in graphs. Okay, so this path was very special, and it has a name. So let's just say M is a matching. It might not be the largest matching, it is just some matching. And this is called an M alternating path. An M alternating path. is a path starting from an M unmatched vertex, like so. There is a vertex that is not matched. Is a path starting from an M unmatched vertex such that every alternate edge is in M. Okay? So subpaths are also alternating paths. Like this is an alternating path. This is an alternating path. This is an alternating path. The whole thing is an alternating path. Actually, a single edge from an unmatched vertex is also an alternating path, because a path that starts from an unmatched vertex. Any questions about the definition? All right? If both endpoints or both endpoints of the path, if both endpoints of the path are unmatched, then the path is called M augmenting. It's called an M augmenting path if both endpoints are unmatched. Any questions about the definitions?
What do you mean by augmenting?
Oh, that's the definition. That's what it means to be an M augmenting path. Like I'm defining an M augmenting path to be an alternating path where both endpoints are unmatched. So this path above is an M augmenting path. This path up to here is not an M augmenting path. They're both alternating paths though. But this is the one that's an M augmenting path.
And when you say alternate edge, do you mean the red edges that point backwards? That are
yeah. But again, at this point, so good. So at this point, let's stop thinking about forwards and backwards, right? Forwards and backwards was merely a mechanism for us to discover these paths. And now we can just talk about paths in the graph without direction, and just any path that has this sort of alternating behavior is called an alternating path. And if both endpoints are unmatched, then the path is called M augmenting. Now let me see if you're sort of following what I'm saying. Suppose you have a matching and you discover an M augmenting path through whatever mechanism. Then what can you say?
That matching is not maximum, right? Because we can add one more.
Exactly. That matching is not maximum. So let's prove the fundamental theorem about augmenting paths. It's exactly this, except it's an if and only if, and that's the non-trivial part. So M is a maximum matching if and only if there exists no M augmenting path. So one side is easy. If M is a maximum matching, there exists no M augmenting path, because if there existed an M augmenting path, you could increase the size of the matching. The non-trivial part is that if there exists no M augmenting path, then M is actually a maximum matching. Like that is not as obvious. Is this statement clear? Any questions about what the statement is saying? Okay? So let me go ahead and prove the statement. So let's start from the easy direction. This is the easier direction. We'll take the contrapositive. Suppose there exists an M augmenting path. Flipping increases the matching. Increases the matching size. Right? So this is the easy part. This is exactly the argument that was made. If you had an M augmenting path, you can flip it and you would increase the matching size. Hence, if M is a maximum matching, there can exist no M augmenting path. Okay, any questions about that? All right. Now let's prove the other side. It's the more trickier one. And again, we'll do it with the contrapositive. We'll say suppose M is not a maximum matching. I need to prove that there exists an augmenting path. I need to prove that there exists an augmenting path. How would I go about doing that? So use a particular trick. I'm going to say, okay, let M prime be a maximum matching. So let's say that M prime is a maximum matching. Consider the symmetric difference M delta M prime, right? Consider the symmetric difference of the matchings. Okay, what is the symmetric difference of two matchings going to look like? If I have two matchings and I take their symmetric difference, and I take all these edges together. So I take all the edges together. If the symmetric difference is throwing you off, then basically what you're saying is anything in the intersection you throw away. Right? And now you've got a collection of, you've got two matchings. What happens when you put two matchings on top of each other? You just draw a picture and maybe you'll see. So here's the red matching. I'm going to draw the blue matching here. Okay, match this over there. I'll match this over there. Match this there. There. So here I have two matchings. What do you get? Suppose you trace one of these along. So start from somewhere. So let's say you start from here. Red, blue, red. Right? So you get this alternating path, and over here you get blue, red, blue, red, blue, red, blue, red. So when you take the symmetric difference of two matchings, what do you get? Any?
You get your augmenting path.
You get something more than a single augmenting path, right? In this case, you got an augmenting path. But let's say that I took this matching here, then what would you get? So by the chat comments, you might as well just say, you get a union of disjoint cycles in path. The symmetric difference, this is a union of M alternating cycles and paths. You get alternating cycles and alternating paths. Moreover, the edges alternate between M and M prime. Right? So you have a union of alternating paths and cycles. That's an exercise. So you should argue that out, but hopefully the picture convinces you. What you do is you simply follow. You follow one of the matching edges. You can imagine following one of the matching edges forward and the other one backwards. Right? And you get a collection of alternating paths and cycles. So the edges alternate between M and M prime. The cycles have the same number of M and M prime edges. Now by assumption, M prime is strictly greater than M, because M is not a maximum matching and M prime is a maximum matching. Hence, there exists an M alternating path with strictly more M prime edges than M edges. Right? Because you started off with more edges in M prime. When you took the symmetric difference, the union is a collection of cycles and paths. One of the paths must have more M prime edges than M edges. It has fewer M edges. This path is M augmenting. Right? This path must be M augmenting. It must have odd length. Right? Because all the paths that have strictly more M prime edges than M edges have odd length, and this path is M augmenting, and that completes the proof. That completes the proof. Any questions?
Sorry, what's I wasn't familiar with what's a symmetric difference between two graphs?
Well, you have two sets of edges. So the symmetric difference contains all the edges that are present in one but not the other. I'll write this over here. So M delta M prime is basically M union M prime. Set difference M intersection M prime. Those are all the edges that are only present in one of them, right? So you take the union and you remove the intersection. Maybe just to draw you the Venn diagram, if that was M and that was M prime, the symmetric difference is the shaded region, right? So you remove everything that is common. All right, so I'm going to pause here. Okay, so what we have proven right now is this theorem about augmenting paths. M is a maximum matching if and only if there exists no augmenting path. Equivalently, if M is not a maximum matching, then there exists an augmenting path. And so the business of the algorithm is simply to find an M augmenting path. And I will repeat sort of what I said about Ford-Fulkerson over here. And this is just a restatement of Ford-Fulkerson. Given a matching M, potentially empty. Consider the digraph. Consider the digraph dm, where so recall that it's a bipartite graph, L and R. M edges are directed, R to L, and all other edges are directed L to R. Right? And that was the thing that I had shown earlier, where the red edges were directed backwards, and the other edges are directed forwards. Right? So the M edges are directed backwards, every other edge is directed forwards, and a directed path, which is in dm, from an unmatched vertex, in L to an unmatched vertex in R is an M augmenting path. Right? And the way to again see that is if you go back to this picture here. Remember that you start with a vertex on the left side. When you go forward, you're going to a vertex on the right side. When you follow the directed path, you're going back to the left side. Then you're going to the right side, then to the left side, and then to the right side. And so what this does is this gives an augmenting path. So any path in this digraph, a path from an unmatched vertex in L to an unmatched vertex in R, is an M augmenting path. And so this gives, I'm just going to sort of state this as an explicit claim that M is not a maximum matching if and only if dm has a path from an unmatched vertex to another unmatched vertex. So this basically then proves that Ford-Fulkerson is doing the right thing, because you say that if M is not a maximum matching, then there exists a path. The path can be found using BFS or DFS. You find the path, you do the flip, then you increase and you keep repeating. And now I will just sort of state the basic bipartite algorithm, bipartite matching algorithm, or the Ford-Fulkerson. So this is Ford-Fulkerson for bipartite matching. So this is the Ford-Fulkerson algorithm. So let's just initialize M being the null set. Then we just run a loop here. We'll say construct this digraph D of M. Let LU, RU be the unmatched sets in L and R. Now we'll run BFS from LU to get a path to RU, If no path exists, then we just terminate with M as the max matching. If path exists, then you flip to increase M. Increase and update M. And that's the entire algorithm. So this step over here can be done in O of M. The BFS can be done in O of M. How many times is the loop going to run? How many times does the loop run?
At most M times.
At most M times. Can you improve the bound? Sure, at most M times. You're right. Why M?
Because the maximum size of a matching could be number of edges. And we get a new edge every time. That's so at least one edge every time.
Good. What is the maximum size of the matching? Can you give a bound better than M? How many matching edges can a vertex participate in?
One.
One. So what is a bound on the number of edges in the matching?
M over 2?
N over 2, exactly. Not M over 2, but N over 2. I missed whether you said M or N, but right. So the matching size is at most N over 2. Right? Because every edge of the matching takes 2 vertices. So, okay, so there is someone who's making something on the screen. I'm going to have to, ask you to stop. So how do I do that?
While you're doing that too, I had a question. Can you speak to why is finding, what is a matching useful for? I mean, I kind of, having heard about this right now for the first time, I kind of understand the algorithm, but not really why.
So I can give you multiple instances of where people use matchings. Kidney donors. So some people need kidneys and other people are donors. And how do you match them up depending on various constraints? Matching algorithms are even used to determine which residents will get into which medical school. So that's like a matching. You have residents on one side and you have schools on the other side, medical schools. And then they use matching algorithms to decide how to pair people up. So of course, in the resident case, it might not be the situation that only one person, one school only takes one resident. But in kidneys, you can obviously imagine this is the case. It also comes into resource allocation. Let's say that R is a set of resources and L is a set of people who want those resources. And you're trying to allocate those resources. Matchings end up being very commonly used there. A more advanced use of matchings is actually in solving systems of linear equations. It turns out that bipartite matching is often used as a subroutine when you want to solve systems of linear equations in elimination, when you're doing some kind of Gaussian elimination or matrix methods. And solving systems of linear equations is everywhere, right? I mean, 90%, or well, I shouldn't say 90%, 80% of machine learning in the end is somewhere solving a system of linear equations. So those are some of the examples for bipartite matching, which appear quite commonly in practice.
Is there a version that maximizes the weight of the edges of the matching?
Good question. Yes, there is maximum weight matching, which I will talk about. You can also say that I want a minimum weight matching. Maybe you want to maximize the size of the matching, but you want to minimize the total weight. Like for example, in the kidney donor case, maybe every edge is some kind of difference between people, and you don't want to actually give the kidney to someone who has maybe a different blood type, unless you have to, or a different, you could imagine putting all kinds of constraints on the matching. And this is the static version. You could have online versions where people are coming and you have to match them. And also the theory of matchings is one of the most fundamental parts of combinatorial algorithms. It appears over and over again, especially in theoretical computer science. Okay, so the matching size is, yes, sorry, someone had a question?
Yeah, so could you, if you have time, could you elaborate on the system of equations thing?
Ask me later. There are certain kinds of block decompositions of matrices that use a bipartite matching as a subroutine.
Okay. And just a quick follow-up. So for the kidney case, wouldn't it be like not exactly bipartite matching, but a stable matching problem?
You probably need a stable, but it's a stable bipartite matching, right? You have donors and you have...
Yeah. Sure.
So it is a bipartite matching with constraints.
Right. Okay, yeah. Thanks.
Okay, so this theorem is that, Ford-Fulkerson computes max matching in O of mn time. Can this be beaten? Yes, there is an algorithm of Hopcroft and Karp that does m root n. Can it be beaten beyond that? It was open for the longest time, and in the past few years there have been some developments where there are new algorithms for maximum matching which use very sophisticated technology and methods from like optimization and numerical analysis. So for now, let's stick with Ford-Fulkerson. I'll probably talk about Hopcroft-Karp next time. But what I want to emphasize right now is that this methodology and technique of using alternating paths is extremely powerful as a mathematical tool. So let me now tell you, sort of switching gears, but is a theorem of Koenig. Way back in 1931, this is one of the, I should not say oldest, there are older theorems, one of the old theorems in graph theory, which says that the maximum matching, the max matching size in a bipartite graph, is the size of the minimum vertex cover. So let's recall what vertex cover is. Vertex cover, so S is a subset of the vertices. S subset of vertices is a vertex cover if every edge has an endpoint in S. So pictorial, a vertex cover looks something like this. So let's say you have S and you have V minus S, then all edges are like this. There is no edge of that form. That is not an edge. So a vertex cover is a set which contains the edges, is a set such that every edge has at least one endpoint in S. Every edge has, I should say, probably at least, because you could have both. That is what a vertex cover is. Question: Can you compute the vertex cover of a graph in polynomial time? Any comments regarding computation of vertex cover?
Are you saying you can because you could still do the maximum matching, which is also in polynomial?
In a bipartite graph. But what about...
Oh, right. Oh, I see. Any graph, sorry.
Okay, so those of you who've taken 104 with me, did I mention vertex cover in 104?
Be complete, right?
vertex cover is NP-hard. So we don't think that there is a polynomial time algorithm to compute vertex cover on general graphs. But remarkably, Koenig's theorem says you can compute the vertex cover. Actually, this proof is also constructive. You can compute the vertex cover of a bipartite graph in polynomial time. But a non-bipartite graph, we don't know. Or we don't think it's possible because it's NP-hard. Okay, so hopefully the significance of this theorem, the algorithmic significance, should, combinatorial optimization or combinatorial algorithms. Here's a combinatorial algorithm. A classic problem which is NP-hard on arbitrary graphs can be solved in polynomial time on bipartite graphs. And what I'm going to do is I'm going to prove Koenig's theorem. Right, vertex cover is NP-hard. Or I should say min vertex cover. Min vertex cover is NP-hard. NP-hard on general graphs. But it happens to be polynomial time computable for bipartite graphs. Any questions about the theorem statement? All right. So this is the proof of Koenig's theorem. So take the maximum matching M. Okay, we're going to start with the maximum matching M. So this is a really beautiful proof. So pay attention, and I think you'll see that there is a real aesthetic value of this proof. Okay, so take the maximum matching. Consider, and let me define LU, RU are the unmatched sets in L and R respectively. Right, so the picture that we have is this is LU, this is RU, and we've got our matching, which we have colored in red. We have our matching. We have our matching over there. So this is exactly what we were doing in Ford-Fulkerson, right? This sort of style of argument. So consider alternating paths from LU that end in R. I didn't say RU because if it ended in RU, then actually it would not be a maximum matching. So consider an alternating path that ends in R. So for example, this one edge is an alternating path that ends in R. But you could imagine something like that, where now this path over here is an alternating path that ends in R. So there are these two vertices that are endpoints. Consider alternating paths that end in R. Let endpoints of such paths be called the set B. Okay, and then consider, I should say M alternating. M alternating paths from RU that end in L, and let the endpoints be called A. Right? This is slightly clunky wording on my part. I mean, the set of endpoints of such paths is called B or A. Okay, so I'm just going to redraw this picture here. With what I mean. So I have LU, they have RU. Actually, let me write out a claim, and then I will draw a picture. And this is the fundamental claim that where we use alternating. One of the claims where we use alternating paths. There is no matching edge from A to B. Meaning, if you look at the endpoints of alternating paths, so you look at an alternating path that starts from LU, it ends up somewhere. You look at an alternating path that starts from RU, it cannot end up at one of these two vertices. Why not? Why not? Does the claim make sense? Does the claim make sense? Yes? No?
I'm still slightly confused what A and B are. Are they like both endpoints of the path?
No. So good question. So let the endpoint on the R side, right? So you start from LU, and you take an alternating path that ends up on the R side. That endpoint on the R side, that's B. And if you did it from RU, then you would get A. Does that make sense?
Yeah, thank you.
Right? So the endpoints on the R side, and I should say the endpoints on the L side. So you start from RU, and you end up with that vertex there. So then this is going to be something on the A side. So these vertices here, these constitute B. And you follow this is going to be in A. But of course, there could be many vertices. Now, hopefully this picture is going to tell you why is it that you cannot have a matching edge from A to B.
Because they're already matched? Or
why can't you have an edge that goes from RU to the opposite side of B, to the matched partner of B?
I don't know how to phrase this correctly, but I feel like it wouldn't be an endpoint, it'd be like part of the path that goes.
Okay, so it's okay to have part of the path because that's also an alternating path. Like a prefix of an alternating path is also an alternating path. Okay, so suppose there was this edge over here. Suppose there was an edge of this form. Let me just draw this. Okay, there was this edge over here that goes there. I claim that there is a contradiction here. There's a problem.
Oh, M's not max matching anymore?
Why not?
You can... I feel like it's because we can flip that alternating path. But
yes,
I lost
exactly.
It.
So you have discovered an augmenting path. The augmenting path starts from there, goes there, goes there, goes there, goes back, goes to RU. And we argue that if it's a maximum matching, it cannot contain an alternating path, an augmenting path. And that's exactly the proof. There can be no matching edge from A to B, because if there existed such an edge, then we can construct an augmenting path. So that's the proof. So suppose there is an M edge A comma B, where A is in A, capital A, and B is in capital B. By definition, there is an M alternating path from LU to B. And similarly, there's an M alternating path. So let me refer to this M alternating path, let me refer to this as PB. Right? There's an M alternating path that ends at B. There's an M alternating path from RU to A, call this PA. The path PB, the edge BA, and then PA in reverse. Like all of this is an M augmenting path. Contradiction. Okay, so that proves this claim that there is no matching edge from A to B. Right, so now let me draw the picture out again. This is LU, this is RU, here is B, and these are the partners of B, and I'm going to just refer to that as M of B. These are the partners of B, and so these are matched here. Then I have the set A. Now we argue that M is disjoint from M of B, so I can draw the picture as follows. This is M of A. And then you've got a bunch of things that are remaining. The remainder, which I will refer to as L remaining, are remaining, and again there's a matching between these. There are all kinds of edges going in between. There are all kinds of edges that are going in between these sets. So I'm going to write out another claim here. And this is key. The neighborhood of MB. So if you look at the neighbors of MB, this is actually contained in B. The neighborhood of MB is contained in B. Why? Can someone sort of give me an argument? Why can't there be a neighbor of MB in RU? Why can't there be a neighbor of MB in MA? Why can't there be a neighbor of MB in R? Any suggestions?
I think it would be kind of the same, because you would have an augmenting path now that would go from LU to B through a matching edge and then back to a non-match.
Right, so if you have there, then you have a contradiction. But what if there was an edge from MB to MA? Then what?
Wouldn't it be the same because they couldn't have a matching edge between them?
That's right, because of the previous claim. There's actually an even more direct proof of this, which is consider edge. So let me write this way. Consider an edge M of B, comma C, where B is in B. So I'm looking at some partner, I'm looking at some neighbor, C. I'm trying to understand where C can go. Now, there is an M alternating path from LU to this vertex, right? So this is B to B. That's the definition of B. So let me refer to this path as PB. Now the path PB, then B to MB, and then from MB to C is also M alternating from LU and ending in R, right? Because this is going to end back in R. But then that's the definition of B. So C is actually an element of B. Because by definition, if you can find an alternating path starting from LU and ending on the right side, that endpoint is in B. So anything, the neighborhood of MB is contained in B. So this vertex C must be contained in here. Analogously, the neighborhood of MA is contained in A. So let me keep this picture here. I'm just going to write this claim out again. And we'll come back to maybe this picture that I will keep on the side. Okay. So the claim is the neighborhood of MA is a subset of A. So the neighborhood of MB was a subset of B. And then we come to our final claim, which completes the theorem. A union B union LR is a vertex cover of size M. Right? Okay, so why is that? So I'm saying that you considered B, then you considered A, and then you consider LR. And I claim this is a vertex cover because any edge has to hit one of these sets. I'm just going to verbally walk through it. If you take LU, its endpoint has to be in B because any edge that is coming from there is basically an alternating path. So if you had an edge from LU to MA, then that would be an endpoint of B. So any edge coming out of LU goes into B. Any edge going out of RU ends up in A. Any edge going out of MB ends up in B. That's the claim. Any edge going out of MA ends up in A. And we'll see that any edge that is going out of R, it doesn't have any other options because we just said that if there is all the edges incident to LU end up in B. All the edges incident to MB end up in B. So all the edges incident to little RR have to go to LR or to A. There's no other option. Okay? So by the way, I'll use N of S is the neighborhood. Is the neighborhood of S, right? This is the notation that I use. Okay. So N of LU is going to be contained in B. That is because every edge is an M alternating path. Every edge, I should say, from LU. So the neighborhood of LU is contained in B, meaning that any edge that's incident to LU bumps into B. the neighborhood of MB, that's the subset of B. That was the previous claim. Similarly, you have the neighborhood of RU. This is going to be contained in A. And we have the neighborhood of MA. This is contained in A. So the neighborhood of RR is contained in LR. There is no other choice because it cannot be a neighbor of LU. We just argued that the neighborhoods of LU is in B. It cannot be MB because we argue the neighborhood of MB is in B. So the neighborhood of RR is in LR. So hence, A union B union LR is a vertex cover. Now a simple exercise is the vertex cover has size at least n. And so A union B union LR is a minimum vertex cover. And that completes the proof. So that proves Koenig's theorem using alternating paths. Koenig's theorem is a fundamental statement in graph theory, one of the early theorems of graph theory, proved in 1932, and now you know it, and you have a proof. And that's another reason why alternating paths are interesting. Not only do they give algorithms, but they also are a very useful technique in graph theory. Any questions at this point? Any questions? Okay. How many of you have seen Koenig's theorem before? Raise your hand. I'm just curious that if you've encountered Koenig's theorem before. Anybody else? Okay. Now, the following. Wait, how long do we go? Is it to 8:45 or is it to what time do we end? Someone?
45.
45. Okay, so we have like 5 minutes left. Okay, so I'll just say one last statement, and then next time we can prove this. An interesting question is, when do matchings exist? And this is now a theorem of Hall. This is another famous result in graph theory called Hall's marriage theorem. And this dates to 1935. So Hall's marriage theorem, this actually is true for general graphs. It says that there is a matching from A to the complement of A if and only if for all subsets of A the size of the neighborhood of S is at least S. It's a very beautiful theorem. It says that as long as all neighborhoods, so one way to picture this is think of this as A, and this is V minus A. And you want to understand, is there a matching from A to V of A? A to V minus A, I'm sorry, not V of A. And this simple condition says you look at every subset, and you look at the neighborhood of the subset. And as long as the neighborhood size is at least the set size, there exists a matching. The proof of this theorem can be done, it's actually a consequence of Koenig's theorem, but it turns out there is also a proof using alternating paths. And that is something that in the next lecture I'll go over. I'll talk about a proof using alternating paths. And then we'll talk about improved algorithms for maximum matching in bipartite graphs. And so with that, I'll end and take any questions that you have.